I work for the same company that I've been with for the past 5 years. I've had four different job positions in those 5 years. The first was a pressurized water reactor
What's the volume button in the corner up there? Is that for
in
you?
Washington State,
You turn that on?
and was a boiling water reactor fuel designer. And now I work at the back end of the nuclear fuel cycle. So once it's done in a reactor, I design how to transport and store it safely. So I started in nuclear analysis, and now I'm more in project engineering. And so I realize I threw a bunch of words in there that may not make sense to you guys, or may just sound totally foreign, like what's a boiling water reactor, pressurized water reactor, what is people. We'll talk a little bit about that, but I also, in general, just want to talk to you guys what engineering is and what kind of options are out there, since you guys are at the beginning of making those crucial life decisions. Do you guys have any questions for me?
Oh yeah. So like, do you get bored? So I don't know. I don't mean that in like a mean way, but like, you were talking about like what you do. So, like, is it every day something new, or is it a lot of times like you're on a computer, or are you, I don't know, out doing stuff? I don't know.
Yeah, so for me, it does vary. When I was doing fuel design, it was the same thing day in and day out. Well, it was different for about 18 months, and then after 18 months, it was rinse and repeat, and you do the same thing over and over again. And that sort of role was a lot of computational analysis, so sitting in front of the computer, writing code, doing number crunching at the end. But that's a very limited scope of what engineering can be. There's also field engineers, people that get out into the field and use their hands and actually turn the nuts and bolts of different pieces of components. There are engineers that work entirely on optimization problems of, how do we arrange the setup in this factory such that the product has to move the least physical distance and therefore has the least likely chance of being defected. So, I mean, within engineering, you've got everything for the people that like to sit in front of the computers and type all day, like the very analytical type, to the more field and implementation engineers that are actually doing work in the field. You also have a whole research side, for the mad scientist sort. Did I answer your question?
Yes, that was a good answer. Do you have your bachelor's, master's? What's your degree?
My bachelor's is in nuclear engineering from Purdue University. My master's will be from the University of Tennessee. I am one semester of research away from having that piece of paper in my hands. So, not yet, but almost. Yep, I chose to get out into the field immediately. College was a great time. You guys have something excellent to look forward to. But for me, it was time to join the adult world and start making money, and I figured I could always go back to school, and I did. So,
Good.
Yep. So I know you guys, I guess maybe a month ago, talked to Disha Patel, who's an electrical engineer.
Yes.
Do you guys have any follow-up questions? Like, what are your conceptions of what an engineer does, or what's available within the science and technology and engineering fields?
But
That's an open question to the class. Do you guys I assume you're in tech ed right now, so I guess a show of hands, how many of you guys are interested in going into engineering or a technology kind of field? Awesome, that's so exciting.
Hey, you get
Great. So I guess I'll talk a little bit more about like engineering course of study, how people kind of fall into engineering or choose it. Engineering wasn't on my radar at your age. I thought I was going to be a doctor or something else, but right about your age, getting into high school, where there really started to be dividing paths between peers, your friends of who's in what math class and what science class, and the AP classes start rolling in. I learned that I was really good at math, and physics was a blast and a half for me. And so those kind of came together, and my physics teacher actually reached out to me and said, you should consider engineering. And to me, that was a foreign concept. It was, what does an engineer do? To me, an engineer drives a train. That's what we learned growing up. But through some job shadowing and some exploration. The Boy Scouts have a program called the Explorers. It's open to both genders, and it allows you, do we have an explorer in the room? Did I see a thumbs up?
Come up here, talk to her. I'm scared.
My God.
Okay, that's all right. You don't have to talk. But so the Explorers program, if you guys, those of you that aren't involved in it, it is not just open to Boy Scouts, but it allows you to, hear speakers like me in a more formalized setting. You get to see them live and in person, and they talk about what they do. And through that, I realized, wow, engineering, I think that might be for me. So I went to Purdue, took the classes. They are very heavy in math and physics and calculus, specifically differential equations. You'll get there. But to me, it was the fact that it was challenging continually, and that was like what kept my interest in it. Some people don't like math and physics, but to me, I guess that's just my type A personality of, oh, it's challenging, and I'm going to conquer this. It's as simple as that. And then I also kind of just fell into nuclear. At a lot of schools, when you go into engineering, your freshman year is just the College of Engineering. You are with 100 or 1,000 other students that all want to be engineers, but nobody knows what type yet. And through usually classes, you get exposed to the different disciplines. There are mechanical engineers who would build your car engine. They build robots. They design power cycles like steam generators and turbines. You have civil engineers that do everything from environmental impact statements to road and bridge design. Chemical engineers do a wide range of things, anything from petroleum mining to cosmetic research, that sort of stuff. There's also computer engineers, electrical engineers, agricultural and food science engineers, industrial engineers, material science engineers. There really are so many different flavors. And to me, it was, a very, cocky 18-year-old Abbey sort of an opinion. It was like, nuclear sounds really hard. That's what I want to do. And so here I am.
You wanted to do something hard rather than something easy? That's a good choice.
Yeah, I mean, that was just, I was really ambitious as an 18-year-old, and I'm still pretty ambitious, but that was the basis of my decision. Was I thought, mechanical and civil, while those are still very prestigious degrees, I thought they were very common. And I thought that being in a niche degree like nuclear would set me apart. It would attest to the fact that, I had different classes and I had a very unique skill set.
Did you ever you were in school or you're
Yeah, can someone closer to the microphone repeat that question?
Bring it on up. Yeah. Go Hawks. Come on, Anna. Stop.
When you were in school, did you ever have doubts of being an engineer?
No, I didn't have doubts until I actually started my career.
Oh.
But those went away quickly. Just like, I don't know, it's about finding your right place. Like I said, there's so many different areas of engineering, and even within a small area like nuclear, there's so many options that it was about finding the right fit for me. The first student that asked the question about, do you get bored? When I was writing Fortran code all day, I got really bored. And that's when I started to have doubts of, oh goodness, I spent, this isn't working for me. So I tried out a new position. I went to a different reactor type, and that was a pretty good fit. I learned some more things, and then I decided, I actually want to be more, big picture engineering of how things fit together, how this works, the design and the licensing aspect. And I found my fit, and I love my job, and I have zero doubts anymore. So I think it's more about, if it doesn't work at first, there's another option. There's another flavor of engineering for you, or there's another role that you can take on. It's all about what fits your skills and your interest. And when you find something that marries those two together, you've got a really solid place to be.
You do a lot of coaching.
Can you repeat that?
do you do a lot of managing? My dad's an engineer. He manages all the time. So that's kind of why I hesitate about engineering.
Yeah, so I mean, it depends. I am what you would call an individual contributor. So I do work. I don't have anybody underneath me. I'm not managing anything. I could stay on this track and become a technical expert in my field of expertise and continue to produce work and create work and write calculations and that sort of thing. Or I could go the management track and manage people or manage projects. I don't have enough experience to, you know, be in one of those roles yet, but I think that's probably the type of role your dad may be in, where he's got people that report up to him. I am not. I'm an individual contributor is the word for that. So producing work that goes up to an engineering manager.
All right, thanks.
Yeah, no problem.
Really good question.
Yeah, those are great questions so far.
I got a question.
Yeah.
Okay, camera.
Zach, who's the guy right in front of the camera?
Why Purdue? Why not any other university?
So, I ended up at Purdue because both my parents went to Purdue. My grandparents went to Purdue, and it was
Legacy.
it was an excellent engineering school. By the time I was applying to schools, I knew I wanted to do engineering. I applied to Rose-Hulman, which is a private engineering school in Indiana. I applied to Purdue University, which is also in Indiana, and I applied to Caltech because I really wanted a school that was about 3,000 miles away from my parents. But ultimately, I chose Purdue because they had a really strong engineering program, and because they had, at the time, one of the top-ranked biomedical engineering programs in the country. And having previously wanted to go into medicine, biomedical engineering seemed like a good fit of those two. So that's why. Plus, Purdue is the best school on the face of the planet, guys. Come on.
Boiler up.
Boiler up, boiler down.
No, baby.
Did you start biomedical?
No, I didn't. So I made my decision by the second semester of freshman year. Most students didn't have to decide until the end of their freshman year which college they would then enter at the end of the year, beginning their sophomore studies. I was applying for a co-op program, so I had to declare which discipline of engineering I wanted in January. And that's kind of when nuclear seemed exciting, because there is also a wide range of applications within nuclear medicine. There's also the power side, and it sounded really challenging and really hard, and I, thought I could be a show-off and do nuclear. So, but yeah, so I declared a little bit early. I never actually ended up in biomedical. A friend of mine freshman year, his dad owned a biomedical engineering company. There's a building on campus, or a wing of one of the biomedical engineering campuses named after him. And I went and shadowed at his company, and after seeing people just, doing research all day long, I thought that's not what I want to do.
What was the hardest class you took? Hard.
Like truly hard would.
Like the math class, like your gen ed stuff, like before you got into your more professional, like.
Oh yeah, so not like history 430. That doesn't count. I hate memorizing dates. I would say the most challenging class I took was reactor statics and dynamics, and it is a very high-level very complicated, complex physics class that you derive by hand the equations that tell you what is happening on the nuclear level, on the atomic level within a nuclear reactor. Solving those equations took about 30 pages of paper, and it only tells you what's happening at that instant. And to give you a frame of reference, in a reactor, you have 10 to the 17th neutrons being created per second. And so this 30 pages of calculation tells you what's happening to one neutron at one point in time. So it's a good thing we have computers. But I would say learning and deriving those equations by hand was the hardest thing I've done.
Okay.
Yeah.
So how much homework is that? Like a night or a week or?
I'd say like that's probably 2 solid nights. I mean, once you start, it's like following a recipe. Like once you have the foundation of the math, the steps just continue to follow. It's not like you get to a point and you're like, oh, I can't do this anymore, and throw the papers up and leave. You know, once you start one of those problems, you just kind of power through.
All right, thanks.
Yeah, no problem. So I also wanted to use a little bit of this time to talk to you guys about nuclear because it is very different. In Iowa, I think you guys have Dwayne Arnold. You guys have one power plant. A lot of states don't have any. So I just wanted to kind of gauge your guys' knowledge of nuclear and kind of talk to you a little bit about that. Because to me, I have no regrets in the direction I went. To me, nuclear power provides clean, safe, reliable, and affordable electricity. And it's one of the best energy sources we have when it's used correctly. So, the first question I guess I wanted to ask is more of a radiation question, a perception of how exposure works. So which person do you think would get the highest exposure to radiation? Is it going to be a pilot, an X-ray technician, somebody who lives right next door to a nuclear power plant, or a dentist?
Dentist. X-ray.
Those are all good. Those are good choices because dentists work with X-rays. They also work with other isotopes. X-ray technicians also are exposed to gamma radiation through the X-ray process. But the answer is actually a pilot. Anybody have any idea why?
I help.
I have no idea.
No, it is solar radiation. Radiation is all around us. It's coming up from the ground through processes like radon gas. It comes to us from natural background like the stars and the sun. What's happening in the sun is a fusion reaction, and you get, every time you take like a cross-country plane flight, because you are, going higher and higher in the atmosphere, you have less protection that the atmosphere provides from the sun to attenuate those particles. So a pilot actually picks up the most radiation in their day-to-day job of those other pieces. So, let's see. When you guys think of nuclear fuel, like the stuff that is powering power plants, what comes to mind?
Uranium.
Uranium? That's an excellent answer, and that's what it is made of. What do you guys, shape, size, color? Is it in barrels? Is it in,
Long rod.
Who said long rod?
Plants.
The football player dude.
Man, some work. Okay, so Scott, I'm gonna try to do a screen share.
Okay.
And show what nuclear fuel looks like. All right, can you guys see that?
Yep.
All right, those are nuclear fuel pellets. They're pretty tiny, aren't they?
Yeah.
Those are actually a ceramic material. If you were to drop it on the floor, it would crack. It's like, yeah, so like your coffee mugs, your toilet, those are all ceramic. These nuclear fuel pellets are also ceramic. They're tiny. I mean, like they're the size of like the top joint on your pinky. But the most interesting thing is they're solid. A lot of people think of nuclear fuel and nuclear waste, and you think of like Little Lisa slurry stored in barrels somewhere. And this stuff is actually physically containable. It's not something that, is liquid and spills and leaks. It's something that is you can physically hold. So, okay, I'm gonna have to reshare again, I think. So.
How many of those little pellets are in a rod?
A bunch. So. Actually, you guys can do this for your work. So each of those pellets is about 0.55 inches tall, just over half an inch. You have 144 inches of fuel in a fuel rod. So you could ballpark it and say 290, but it's a little bit more than that. All right, so this is a fuel rod. They are skinnier than your pinky, and they are 13 or 14 feet long. But there is 12 feet of fuel pins, of the little fuel pellets are all in there. And then at the bottom and top, there are springs internal to it because they're exposed to really extreme temperatures and pressures to create energy.
Are those depleted rods?
No, those are fresh rods.
Ooh.
So the other thing is that that fresh fuel pellet like this, you saw the gloved hand was holding them. Fresh uranium you can hold, you can touch. It is non-reactive. It is a safe material to handle. Once it's been depleted, as you said, or we call it spent or used or irradiated, then it is no longer safe to handle by normal handling means. So let me get out of here and find another picture for you. So once it's in those rods, it gets put into what is called a fuel assembly. And you can see, do you see this picture?
Yeah.
All right. So this is a fuel assembly, and you can see at the bottom, it's a cutaway, so you can see what the insides look like. But it's a square array of these rods. And that's what that's how they look. And so during the manufacturing process, you end up with a final product that these guys inspect. These guys are looking for small little particles before they ship it out to a nuclear reactor. So that's what a fuel is. This is what nuclear fuel looks like, guys. Exciting, right?
Yes.
So if you guys stop seeing me changing pictures, let me know. Okay?
Where do they manufacture those at?
So they manufacture in the United States. My company manufactures these in Richland, Washington, which is where I worked for a small bit of time. And here's what the manufacturing floor looks like there. If you look on the right, you see those little grids that are kind of long, or I guess they look like that's where fuel assemblies would sit during construction. Over on the left, you see a big yellow blanket. Do you guys see the yellow blanket on the machine?
Yeah.
Okay, so that is an X-ray machine. All of the fuel is X-rayed before it gets sent out because you're looking for little defects. You know, if there was a tiny little piece of anything inside that fuel assembly before it gets shipped to the customer, it could cause damage and it would be unsafe. So what they do is they X-ray the fuel assemblies to make sure that there's nothing in there once they're complete. So let me get one last picture before we just start talking about power and energy. Let's see pictures. So once these assemblies end up on site, they are loaded into a nuclear reactor, which is like this. It is bright blue because there is used fuel in that underwater. So there's probably 40 feet of water that these gentlemen are standing on, and that tool that is coming down from the crane in front of them is a fuel handling crane. It will go down into that 40 feet of water and grip onto a fuel assembly and lift it up and move it. So does anybody know why the water's blue?
Yes. I like that question. I got a question.
Okay, go ahead, shoot.
Like how much power, what could you power with one of those, just one of those little pellets?
That's an excellent question. So in terms of watts, that's hard to
Kilowatts.
yeah, so okay. I guess I know more the energy equivalents. So a single pellet is equivalent to a ton of coal. 2,000 pounds of coal is equal to a single one of those little pellets. And it's also equivalent to about 16,000 cubic feet of natural gas. That is how energy dense uranium is.
Wow.
Yeah,
Okay.
and I want to say it's so it's a ton of coal, 16,000. I want to say it's also like 600 barrels of oil. It's ridiculous numbers. I mean, it's just unbelievable how much energy capability is in a single nuclear fuel pellet. So there's a lot of energy in there. That was an excellent question. But so as the nuclear process happens, you end up with alpha particles, beta particles, gamma particles, electrons. They're all flying out, and they're contained in this nuclear reactor. That's how we keep the public safe. It's how we keep the plant personnel safe. 3, 4, 5, 6 feet thick steel and concrete, and it's a pressure vessel, so it keeps it all contained in there. But what happens is once the uranium has fissioned and it's shooting out these particles, the electrons are moving faster through water than light is moving through water. And it's moving fast. That delta is about the wavelength of blue light. That's why you have the blue glow. It's called Cherenkov radiation. So it's kind of interesting. So we think, we typically think of nothing travels faster than the speed of light in a vacuum. You'll learn in your physics classes, but in different mediums, some things can move faster than the speed of light. In the case of these high energy electrons, they are zipping through water faster than the speed of light, and they're emitting this blue wavelength of a glow. So after the reactor is done operating, can you see this picture?
Yeah.
Okay, so this is different. So if you know the nuclear reactor, it's a circle. The fuel is loaded in a circular pattern. In the spent fuel pool, once the fuel is done being used, it goes and it stores under about another 40 feet of water for about 10 years. So can somebody guess how long nuclear fuel is used before it goes to this pool? Any guesses?
20.
There's no wrong answer.
20 years.
Not quite.
It's a 15.
It is about half that. It's between 6 and 7 years, but it's a long time, much longer than other fuel supplies. So the way a nuclear power plant works is it comes online, it starts producing power, and it will produce power for 2 years. It's called baseload energy when you produce a lot of power 24/7. Not like coal plants or gas plants or solar. When the sun goes down, we can't get power. Wind, when it's not windy, we can't get power. This produces electricity non-stop for 2 years. And then they shut it down. And then they swap out about a third of the fuel. And they bring 1/3 in fresh, and the other 2/3 they rotate. So each fuel assembly will get 3 cycles of operation, so about 6 years before it goes into that pool, which is incredible. If grain cars full of coal don't come up to the coal power plant, they don't produce power that day. They need new fuel every single day. Natural gas can be stored, so they can go a while without having, refuel, but maybe we're talking days or weeks. Nuclear is something that you flip the switch, and it goes for 2 years. It's pretty incredible. So, but there is an importance to having a mix of coal, oil, and gas and solar on your grid, just like, we've all learned you don't put all your eggs in one basket. Having a diversification of energy sources is important. Nuclear provides kind of that backbone, that stable, reliable electricity. Coal is really cheap right now. Coal is really quick to build. If you need more electricity in a certain area, coal is very, very easy to build and to produce. Same goes with natural gas. Natural gas is very, very cheap right now, so it's a very great source of energy. So it's about having kind of that mix, but nuclear is very unique from the other sources. But outside of the fuel type, all these power plants are really the same, whether it be a coal plant, a gas plant, or a nuclear power plant. All these plants are trying to do is, why can't I open up a web browser? But ultimately, all these plants are trying to do is boil water to create steam, to turn a turbine, to spin a generator, and that generator produces electricity and it